Welcome to my YouTube channel Mechanical Magic Mechanical Learning Tutorials. So in this video I am talking about some of the simplest calculation of a Otto cycle. So let us see, the data is given to you. Determine the compression ratio, the cycle efficiency and the ratio of maximum to minimum pressure in an air standard Otto cycle. The minimum temperature is 25 degrees centigrade, maximum temperature that will be equal to 1500 degrees centigrade. Heat supplied per kg of air that will be equal to 900 kilojoule. Take the specific heat at constant volume process, or you can say CV, that will be equal to 0.718 kilojoule per kg Kelvin, and take the value of gamma that will be equal to 1.4. So this problem generally you can see into the various universities, and I am taking these problems for the Gujarat Technological University January 2010 from the 7 marks of question from heat engine chapter. So let us take out the given data. So determine the compression ratio, so R, the efficiency and the ratio of maximum to minimum pressure of an Otto cycle. So minimum temperature 25 degrees centigrade, so T1 25 degrees centigrade. So now it will be converting into the Kelvin, so 298 Kelvin. Maximum temperature of the cycle, and that will be equal to 1500 degrees centigrade. So as from the Otto cycle, the maximum temperature you will find onto the 3 points, so that will be representing T3 as a 1500 degrees centigrade, so 1773 Kelvin. Then the heat supplied per kg of air, that will be equal to 900. So Q supplied, that should be equal to 900 kilojoule per kg Kelvin. M is equal to 1, so 1 kg of mass. CV 0.718 kilojoule per kg Kelvin, and the value of gamma, that will be equal to 1.4. So let us see onto the PV diagram of this data. So x-axis will be representing as a volume, y-axis it will be representing as a pressure. So this is your Otto cycles. So problem in the case of Otto cycle, that will be, you can say in simple way, constant volume heat addition and constant volume heat rejection process. So 1 to 2 process, that will be representing as a adiabatic compression process. 2 to 3, that will be constant volume heat addition process. 3 to 4, that will be also representing as a adiabatic expansion process. And 4 to 1 process, that should be equal to constant volume heat rejection process. So from the PV diagram 1 to 2 and 3 to 4, it will be representing as a adiabatic process. So that will be follows PV raised to gamma equal to constant. So as from the PV diagram over here, V1 equal to V4 and V2 equal to V3. So let us start with the calculations. So from the given data, Q supplied, that should be from 2 to 3 process, or you can say constant volume process. So Q 2 to 3, that means M. CV means constant volume process. So M CV into T3 minus T2. Just put the value of Q 2 to 3, that will be 900. 1 kg of mass, value of CV from here. T3, it will be given to you the maximum temperature over here, and T2. So you will find out the temperature of second point over here, you can say end of adiabatic compression process. So T2 equal to 519.52. Now first one, the compression ratio, that should be equal to R is equal to V1 upon V2. So from the process 1 to 2, that will be the adiabatic process, or you can say adiabatic compression process. So T2 upon T1, that should be equal to V1 upon V2 raised to gamma minus 1. So V1 upon V2, that will be equal to the compression ratio. So R is equal to T2 upon T1 raised to 1 upon gamma minus 1. So just put the value of T2 over here, T1 from here, and you will get the answer of the compression ratio. R is equal to 7. So that will be the answer number 1. Now ratio of the maximum pressure to the minimum pressure in the cycle. So maximum pressure you will find over here. So that will be the P3, and the minimum pressure you will find at P1. So as from the adiabatic process, P1 V1 raised to gamma equal to P2 V2 raised to gamma. So P2 that will be equal to P1 into R raised to gamma. So P2 that will be equal to 15.23 into P1. So now from the constant volume process over here, or you can say 2 to 3 process, P2 V2 upon T2 that will be equal to P3 V3 upon T3. So V2 equal to V3. So V2 equal to V3. So finally you will get P3 equal to P2 T3 upon T2. So just put the value of P2 from here. So that will be 15.23 P1 into T3. That will be from the given data over here, and T1 from here. So finally you will get P3 equal to 51.98 P1. So P3, just you can take out. So P3 upon P1 that will be equal to 51.98. So that will be the second answer, or you can say the ratio of maximum to minimum pressure in the Otto cycle. Now the air standard efficiency of the cycle that will be equal to 1 minus 1 upon R raised to gamma minus 1. So just put the value of R from answer number 1 and you will get the answer. Efficiency of an Otto cycle that will be 0.5408, or you can say 54.08%. So that will be the answer number 4. So hope you understand it, like it and subscribe Mechanical Magic, Mechanical Learning Tutorials. Thank you.